Hey everyone, welcome back. In this video we're going to be looking at polynomial inequalities and essentially answering this question. How do we determine when a polynomial is positive, negative, or zero? So we have seen this before towards the beginning of the year, but we're coming back to it again because we just recently learned additional factoring methods for higher degree polynomials. So let's just review real quick exactly how we go through just this process. So let's say we have a function, a quadratic function, x squared plus 4x minus 21, and we would like to know when the function is less than 0. So we would write our situation as our quadratic equation less than 0. The very first thing we're going to have to do to examine this problem is to factor. Okay? So beginning with that, if it's not already factored. So factoring this, we get x plus 7 and x minus 3. Okay. The reason for finding the factors is that we need to know the zeros of the polynomial. So the factors show us the zeros. So we would say the zeros are negative 7 and positive 3. And something to note at this point is that according to our inequality symbol, we are looking at open brackets. So this is going to be more of how we represent our answer, but according to our symbol, we're looking at open brackets. Okay. So once we've found the zeros, we now want to perform the interval test. So the interval test, we place our zeros on a number line, so negative 7 and positive 3, and we know that negative infinity is on the left, positive infinity is on the right. So we select within each of these 1, 2, 3 regions, we want to select a number. So let's say we select, I don't know, negative 8, we can select 0 here, and we can select 4 in this far right region. These are going to be our test values. So reviewing, we place each of these back into the factored polynomial, and we want to know, will each factor be positive or negative? So as I place negative 8 back into our equation, we get a negative number from the first factor and a negative number from the second factor. So the product of two negatives we would write as a positive. So let's try the next one. So when I place 0 into this, we get positive and a negative. And when we have an odd number of negatives, the result will be still negative. Placing a 4 in, so we would get positive. We would get positive on the second factor, and as we get two positives, we still, when we multiply, have two positives. And this is the moment where we have to go back to our initial problem and look at the scenario that we have. So we have less than 0, and essentially what is that telling us is that we want to know when the function is negative. That's essentially what we're looking for. So in our interval test, we want that region. And we had said we're using open brackets, and we want the negative region, which is this region here. So our solution set is open bracket negative 7 to positive 3. So every x value within this region will make this quadratic equation less than 0. And that is exactly what we were looking for. So let's try this again. So let's imagine we have this polynomial. X minus 4 quantity squared and x squared minus 1. Okay, and we are looking for when this polynomial is greater than 0. So it's the same 3 steps: factors, zeros, interval test. So we want to factor all this out so we know that we have essentially 2 factors of x minus 4 and x squared minus 1 factors to x plus 1 and x minus 1. Okay, so we factored, now we would identify the zeros. So we would have positive 4 again, negative 1, and positive 1. And this is typically the moment where I will look at the inequality symbol to determine whether or not we have a closed or open bracket. And I just realizing this, I wanted to make this greater than or equal to 0. So having greater than or equal to 0, we're going to have a closed bracket in our solution set. Okay? So now we perform the interval test. So our interval test, we would have negative 1, 1, and positive 4, with still negative infinity, positive infinity on the right side. Selecting our test numbers. Again, what I'm choosing, you could easily choose a different value as long as it's in that region. So I'm choosing negative 2, 0, 2, and let's say, I don't know, 6. So when I place negative 2 in, I'm not going to write down what I did last time. I'm just going to do more of that mentally. So I'm going to place negative 2, we get a negative, a negative, a negative, and a negative. So an even number of negatives results in a positive number when multiplied. So now I'm moving on to 0. So I'm going to place 0 in. Negative, negative, positive, negative. So I had 3 negatives and 1 positive, which will result in a negative number. Placing 2 in, negative, negative, positive, positive. So we would get positive. And then placing 6 in, we would get positive, 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 positive. Okay, so we saw here we have closed brackets at negative 1, 1, and 4. And based off of our initial problem, we are looking for when our polynomial is greater than 0. So greater than 0, that means we want positive values. So we would have, therefore, this region, we would have this region, and we would continue on to this region. Okay, I want to make a note here. If we had open brackets, what we would actually have is we would have from 1 to positive infinity, but we would have had to skip over 4. So it would look like 1 to 4. We would have to skip over 4 and go from 4 to infinity. So there'll be an example here that will have us, actually needing to do that. But in this case, we can use 4. 4 is a possible answer. So our solution set is negative infinity to negative 1, close bracket, and then we jump up to positive 1 to positive infinity. And that would be any number within that interval makes our polynomial greater than 0. So if you have any questions or comments regarding this skill, I'm adding a few additional things here, but if you have any questions, post them in Google Classroom, and I'll do my best to answer them before you enter the class next day. So, our last example, yes I said last example, is something of a higher degree. So let's say we have, this this quartic equation, this equation with a degree of 4. Notice now we can't really easily factor this. So this is where our new methods of factoring are needed. So we want to determine exactly when is this polynomial greater than 0. So on our interval test, we were looking for positive values. Okay? So before we even get that far, we need to basically just factor this. This needs factored. Okay, so if I performed the Descartes rule of sign that we discussed recently, we would see that there could be the different possibilities. We could have 2 positive roots, 2 negative roots, and no imaginary. And so 2 positive or no negative, leaving us with 2 imaginary, or the opposite, no positive, 2 negative, 2 imaginary. And lastly, and probably the most uncommon, is having neither positive nor negative and all of the zeros be imaginary. So if you were to pause the video and perform Descartes' rule of sign, this should be the table that you get. And then also, looking at the possibilities in terms of rational zeros, our p's and q's, our factors of our constant would be, okay, so these are the factors of 48, and then the factors of 2. Okay. So when we divide, when we actually list out all the possibilities, we get this list. And as we've discussed before, we test 1 to see if 1 is a 0. So through synthetic division, so that would give us, we would have 2, negative 3, negative 24, positive 4, and 48. So going through this, we find and already I'm thinking this is not going to work for us. Yeah, it's not going to work for us. So no, not a 0. Okay, so let's just happen to try. I wonder if 4 is a 0. Okay, so out of all my lists, I just decided to choose 4. Let's say 2, negative 3, negative 24, 4, and 48. So we would have, so you drop the 2, positive 5, 20, negative 4, negative 16, negative 12. Oh, interesting, we get negative 48. How about that? So this is a 0. So x minus 4 is a factor. So this is going to be one of our factors. Next one. So we keep going. I wonder if negative 2 is a factor. So 2, 5, negative 4, negative 12. So going through this real quickly. 2, negative 4, we get 1, negative 2, negative 6, positive 12. Excellent. So yes, x plus 2 is a factor. And if I'm thinking correctly, we went from a degree of 4 to a degree of 3. Yeah, degree of 3 to a degree of 2. So we now have a quadratic. So I'm going to stop synthetic division. So now we have 2x squared minus plus x minus 6. And this does factor 2x plus, minus 2x minus 3 and x plus 2. Leaving us with a factored polynomial of, I'm just using f of x, wasn't really labeled at the beginning. So x minus 4, x plus 2, we have another x plus 2, and 2x minus 3. Okay, giving us zeros of positive 4, -2 and +3/2. Okay, so our interval test, now that we're ready for it, we would have -2, 3/2, +4. So I want to use -3, 0, 2, and 10. Why not? Okay, so testing each. And with -3, we find that we get a positive product. With 0, I'm going to place 0 back in, we find we get a positive product. So let's just showing that real quick. 0 placing it into each. Negative, positive, positive, negative. So 2 negatives, 2 positives result in a positive. Placing 2 in, we find we get a negative region. And placing 10 in, we find we get positive, 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 and positive. Alright, so in this problem, paying attention back up top, we have just greater than. So I would have written it right here. We have open brackets. So at each of our zeros, we have open brackets. That's going to make a difference, and you'll see why. We wanted positive values. So the regions that we desire are going to be this region, and from this region to the left, giving us a solution set of -infinity to -2, but being an open bracket, we have to skip over it because we cannot use it in our function, in our polynomial in this situation, to 3/2, and then from 3/2 moving up to 4 to positive infinity. And that is the solution set. So any x value within this region will make our original polynomial greater than 0. And the reason again why we could not just continue through -2 is because we found that that -2 is a 0. And remembering what a 0 is, a 0, if placed into the polynomial, sets the polynomial equal to 0. And we only wanted it greater than 0, and which ruled out this value. So this is our solution set. So before you come into class, I would like for you to solve one last problem. So before we meet again, I would like for you to, given our function, determine the x values for which make the function less than or equal to 0. Okay?